Okay, I'm going to talk to you today about computer basics. We're just going to cover some fundamental concepts in computers. I don't know what kind of background everyone has that might be watching this, or if they've already had a class that kind of discussed these things in detail, but I just wanted to give a quick overview of what is a computer and what's inside of it, what makes it tick. And so if you look at any computer system that's modern today or one that's been around in the past 3 or 4 decades, they're all going to follow what's called the von Neumann architecture. And this just simply means there are four main pieces to it. You have the CPU, which is actually the computer part. It's the chip that makes the computer go. And then it also has input and output pieces that get data in and out of the computer, and also the memory portion, which allows us to store information in it as well. And then, of course, on top of all of that hardware is the software that makes the computer run as well. So you've got your architecture, CPU, input, output, memory, and software, and that's basically a computer in a nutshell. But who the heck was von Neumann? Well, he turns out he was a genius. Okay, he lived in from 1903 to 1957, and he's on par with the likes of Albert Einstein as far as the level of his genius. He was started out as a mathematician, but he also worked in the field of physics. Um, He made contributions to economics and statistics. He helped to invent the atomic bomb and nuclear energy. And, of course, as we saw today, the von Neumann architecture is named after him. And so he contributed to digital computing as well. Before von Neumann architecture, computers were specialized machines that they were built for one single purpose, and they were not easily reprogrammable to do multiple things. And so he helped to change all of that. So that's the von Neumann architecture. And like I said, any computer system that you can think of today kind of follows this setup. Even the simplest computers. And if you think about it, computers are everywhere. We have we're just adding CPUs and computer systems into everything. So, for example, you think about in the car, in the automobiles. Now we have anti-lock braking systems, and what these things do is it puts a computer in your car to help you from skidding out of control on a slick surface, or when the road is wet, or like in the wintertime like it is right now when you get snow and ice on the road. Before this system, they taught drivers that you need to pump the brakes when you're trying to stop on a slick surface. You need to pump the brake pedal real fast, and that keeps the wheels from locking up. Because once they lock up, once the wheels stop turning and you go into a skid, then you have no more control over the car. So the idea is that we put a computer in, and the computer can pump the brakes way, way faster than a human being can, like 30 or 50 times a second. So there's a sensor, and then that sensor monitors the progress of the wheel. It's spinning at a certain rate, and if that rate changes or stops turning, it goes from turning real fast to not turning at all. That information gets sent to the CPU of the anti-lock brake system, and then the program that's running in that says, oh, I got to do something here. So then it sends an output message out to the braking system and controls the actual hydraulic system that applies pressure to the brakes on and off much, much faster than a human can. And it helps you to maintain control of your automobile in the wintertime. So we have systems like that, but just about anywhere you can think of that has a computer in it, it's going to follow this same basic architecture with the CPU, the input-output, some memory, and some software that's running on it. So yeah, all of the Internet of Things items out there would follow this. So ebook readers, Kindles. What are some of course our iPhones, our smartphones that we carry around in our pocket? They're full-blown computers in our pocket nowadays, aren't they? But even appliances, televisions now, our smart TVs, they have this same thing going on. But even household appliances are starting to have this now, washers and dryers and refrigerators. And not only are they having a standalone computer system with the CPU input, output, and memory and software, but they're also, many of them are having wireless network connectivity as well, so they can not only operate as a computer internally, but they can connect with other computers. And that makes things, that's what basically the Internet of Things is. Not only did we put a computer into an object and computerize it, but now we've allowed it to connect to other computers too. And you can remote control things now. You can turn your lights on and adjust your thermostat from your phone and things like that. That's all what the Internet of Things is all about. Okay, so back to the CPU. That's the main chip that runs everything in the computer. It's divided up into two parts, the ALU and the CU. So the arithmetic logic unit is responsible for the math part of the operation of the computer, and then the control unit does everything else. It controls all of the functions. It follows the instructions of the software that's running. It responds to interrupts that come in. If there's a new condition from input and output that demands its attention, then it's the control unit that switches control of that. So, but that's the microchip. These have gotten more and more powerful over the years. There's a rule out there. What's the rule now? I didn't put it in the slides and I can't think of it. Doggone it. It's Moore's Law. Moore's Law, that the computers will become 10 times faster, and I need to look that up. Somebody look up Moore's Law for me, so next time I go through this, I'll know what the heck Moore's Law is. But basically, computers are going to double in speed every year, every 10 years, something like that, and it's followed that. They keep getting smaller and smaller and faster, and just when they think it's going to stop and that we can't increase our computer power at the same rate anymore, they make new breakthroughs in physics, and they find new ways to keep things going now. And so, but that's the CPU. You should be familiar with this name, Jack Kilby. So Jack Kilby, we're proud of Jack Kilby here in Kansas. He was born and raised in Great Bend, Kansas, and he grew up here. And he went away to college and made a name for himself at Texas Instruments in Texas. But he got his start in his dad's home in Great Bend, tinkering around with radios and stuff on the farm. And that's when he decided to become an engineer. So if you visit Great Bend, Kansas, be sure to visit the courthouse, the town square, and see the big statue in Jack Kilby's honor, because he invented the microchip. He was an early inventor in the computer industry, and thanks to him, we have the mobile computers that we have today. And it all got started here in Kansas. So he lived from 1923 to 2005, and he won a Nobel Prize. So another genius individual. So all computer chips are made out of silicon. This is a picture of a silicon wafer. It uses a photographic imaging process. So once they design how the chip is going to work, they shoot light onto a photosensitive substrate and kind of burn these circuits into the silicon chips. Then one wafer like this gets cut into many, many microchips that then get packaged and sold as CPU chips. This is the motherboard. The motherboard's the piece of electronics that you put the CPU onto, and so that's how all of the things outside of the CPU will connect to it. So in any of your input-output devices will normally be connected into the motherboard through various ports and input ports and output ports. All right, then we have the software. I like to boil things down so they're simple. All computers, all computer software that is written does one of these few things, loops. So computers are very, very good at doing things over and over and over again, just like we saw in the automatic anti-lock braking system. It applies and releases the brakes many, many times much faster than a human being can do. Computers don't get tired of repetitive tasks either. So that's what loops are in software. They just do something over and over again, and computers are very good at that. Computers are also really good at making decisions. Again, a computer can analyze data and make a decision based on the data much more quickly and much more reliably than humans can. So that's why we have things like automatic pilot systems, and we're working on autonomous vehicles. Actually, human beings have very, very sophisticated thought processes. It's hard to replicate what human beings are able to do in a computer. But once you can boil it down to simple yes/no types of situations, then the computer can take over and it can decide a yes or a no question based on the data that it has much faster than a human can. But just deciding yes or no to something can be done very quickly inside of a computer also. So we've got loops, we've got decisions, we also have our input-output, which we talked about in the von Neumann architecture. Software handles data coming in and data that gets sent out as well. And then another thing that software has to do is read from memory and also store information into memory that we want to use later. And then finally, software does the math. So that again, that happens in the arithmetic processor part of the CPU, or the arithmetic logic unit, the ALU part of the CPU. That's where the math gets done. Okay, so loops, decisions, input, output, do something with memory, and do some math, and there you have it. That's basically what every computer does, and that's how the programs work. And so then it just takes many, many years of practice and learning to get really good at writing the software for whatever application that you have that you want the computer to do. One of the big advances in computer programming, computer software, was the invention of the operating system. Okay, so when I was a youngster and in high school, we used the TRS-80 system. And I think there was a simple operating system to it. It was like mostly just a disk operating system, a few simple commands that you could give it to read information from a disk and things like that. But nothing like what you see today with a graphical operating system, or a GUI, they call it, graphical user interface. It was just respond to information from the keyboard type set of commands. Most of the time, if you didn't know what you were doing, you would see the error, syntax error, because you were typing commands it couldn't understand. So you had to type the right words to make the thing work. The operating system changed all of that. So this is the system that runs on top of the CPU and allows the computer to provide you the environment that you know and love today, whether it's a Mac system or a iOS mobile system or Linux system. Androids run versions of Linux, or Microsoft Windows. All of these are different operating systems, and other people there are always new operating systems being developed out there, but these are the kind of major ones that are out there right now. But the main thing is that they do is they allow human interaction with the computer. And they just kind of help organize it, and they control the internal functions of the computer, and give a nice interface for human beings. All right, then we have the input-output part. So anything that a human is going to touch or use or look at based on the computer, these are input-output devices. So your screen, your touch screen, your mouse, your keyboard, your floppy drive. Nobody uses floppy drives anymore. Your flash drive, your hard drive, your solid-state drive. What else is there? And a network interface, like you hook up a network wire, Cat5 wire, or a wireless connection going over Wi-Fi. All of those are input-output devices. But we also have printers. You have a piece of hardware that plays sound, the sound card or the sound chipset. That would be an output device. But there are specialized tools too. If you go in a machine shop, they use CNC, computer numeric. So what's the CNC? Cutter? Computer numeric cutter, I think. Computer controlled manufacturing is what that is. Robots, robotic arms. All of these are output devices. Anything where we get a useful result from our computer, that's the output. If you think about that anti-lock braking system, the output part of it goes and connects to the braking system, and ultimately we get the result of the car stopping from the output. And the input going in would be the sensor that senses the wheel rotation. All right, so that's input output. Oh, I have a slide here just about the basic. Why do we have the keyboard on a typewriter originally and now on our computers laid out the way they are? This little video, there's a link to it that you can watch that separately. Goes into more detail on why that came about and why we still use the keyboard the way it is. I have a hunch that keyboards are kind of on the way out. Voice recognition software has gotten a lot better. People are interacting through touch screens and a lot of other different ways, and actual keyboards are becoming more and more less important. But if you're interested in seeing how the keys got arranged the way they did, check that video out. Video cards, connecting to monitors and displays. These are actually they're another form of a CPU, or it's a video processor, a coprocessor. It works alongside of the CPU, and its entire function is to manage the display. So we have, especially when the computer is rendering 3D graphics or processing video, a lot of that is processor intensive, and you would tie up the CPU if you didn't have another processor dedicated just to the video part. It has its own memory as well. So those of you that are gamers like to look for the best video card and chipset to put in your system, so you don't get any lag, you don't get killed because your computer's too slow. So that's video cards. Also displays, cathode ray tube. That's the good old-fashioned ones. Probably most of you are old enough to at least remember in your early days of school possibly having the old-style TV set with an actual tube, a picture tube inside of these displays. Great big honking heavy monitors. But it didn't take long for us to replace those with the liquid crystal displays, or a LE type of display, or some kind of touch screens even, or on our phones and stuff. They've shrunk down. The picture keeps getting better and better every year, but ultimately it's just about showing us pixels on a screen so we can see what's going on with our computer or inside our phone. The network interface, the card or adapter, it's either a chip. In the old days of computing, you had to take your cover off of your computer and put an expansion card in if you wanted network connectivity. I did that many times. You'd have to install software drivers to make that thing work, just because it wasn't assumed that every device you would buy would want to come with a network connection. So that was an add-on feature. But now it comes with virtually everything. All of our mobile devices have Wi-Fi or wireless interfaces on them. But this is another form of input-output that specifically connects to networks. Also, if you have a cell phone, it'll connect to the cellular tower, and data can run over that as well. And also Bluetooth would be another form of wireless radio connection for a short range connection. Other types of I/O ports, well, we already mentioned Bluetooth. The really old stuff, the parallel port, you would hook a printer up with this big cable with lots of pins on it. Serial port, and most famously right now, the USB port. HDMI port would be another one that's used for video connection. We've got memory. Two types of memory, volatile, non-volatile. What's a volatile personality? You just never know what's going to happen with a volatile personality, do you? They catch you off surprise. They might be sweet one moment and just explode on you the next. That's what volatile means in people. Well, volatile memory is kind of the same way. You don't know what you're going to get. Should the power drop off, you're not going to have memory anymore. Volatile memory is good as long as there's power applied. As soon as the power goes out or you shut the computer down, everything inside of volatile memory goes away. So originally that was basically your memory, and then they developed read-only memory, which you could burn information into a chip, so it would be non-volatile. That means that the information would remain after the power turned off. But read-only memory means it was programmed in the factory and you couldn't change it. Okay, so you couldn't write anything to it. So you had RAM and you had ROM, but now we've got kind of hybrid types of memory that's somewhere in between volatile and non-volatile. It's not volatile, that is, it doesn't go away when the power goes off, but we do have the ability to read and write to it. So some examples of non-volatile memory would be like your SD cards that go in your cameras, your micro SD that goes in your phone. PC cards, that's a really old one that they used to use in laptops and Palm Pilots and various handheld devices. I haven't seen one of those in quite a few years. But flash drives, jump drives, the kind that you carry on your keychain and you plug into a USB drive, that would be non-volatile. They're not perfect though. Don't store only one copy of your report or your term paper that you're working on, or your big project that you've spent many hours. You want to back up any data that goes on your flash drive, because they do fail from time to time. They're not perfect, but they, in theory, are non-volatile. In fact, that they keep your data even when there's not power applied to them. A hard disk drive was an early form of non-volatile memory that had large capacity storage in it. So it was a disk that would spin, and it used a magnet to make the little ones and zeros on it to store your data. And nowadays we have solid state drives, which are a larger form of flash drive. But you can get a computer with this built into it, or you can get removable ones that you hook up to it. But it does not require power to retain the data that it stores. Volatile memory would be like RAM or dynamic RAM. Random access memory is what RAM stands for. Again, you have to have power to make this thing work, and as soon as the power goes away, then the information in there goes away as well. The nice thing about this, and why the RAM or the DRAM is important, is because it's fast. It's much faster to read and write to this type of memory. This is what the CPU likes to interact with. If you're pulling information out of long-term memory, say your flash drive or your hard drive, something like that, you want to pull it off of the disk and bring it into RAM so the CPU can read and write it really quickly. But the downside is it's more expensive too to have this type of memory. Per megabyte or per gigabyte, you're going to pay more for your RAM than you are for your solid state drives, or and if you really want to bargain, buy a hard disk drive now, because you can get gigabytes and gigabytes, terabyte drives for very affordable prices these days. All right. Well, I think we've covered all of the basic components and parts. That should give you an overview of what computers are made of and what's inside there, what's important. But I put this slide on here as well that just think about how far we came. So this is we just completed the 50th anniversary of the Apollo landing last summer, and so now we're into 2020. We're starting a whole new era, I guess you will. 50 years of having gone to the moon. And I put a little link here. There's an article that you can read too about that. Just a quick overview. If you compare the computer that helped land the Apollo on the moon compared to what everybody's walking around with in their pocket now, the differences are staggering. In 1969, the Apollo guidance computer had 32K, that's kilobytes, of RAM memory. Okay, so that's the volatile type of memory. And then it also had 72 kilobytes of ROM memory. So that's the pre-programmed, non-writable type of memory that had the program in it that helped get the rocket ship to the moon. Okay, so less than 1 megabyte of memory. And now we have 256 gigabytes of memory in our phones, and we fill them up so quick with lots of pictures and media and stuff. At least I do. The other day I've got like a couple of iPads lying around and an old iPhone and I don't know what, my computer has a solid state drive in it. Just all of these things. Even Google, Gmail was telling me you've used all the space that we provided you, and Apple, all of these cloud storages. I fill all this up because I take lots of pictures and movies and stuff. But anyway, it doesn't matter how much they give me. It seems like I fill it all up. But can you imagine just landing on the moon with less than 1 megabyte of data? But compared to what we do now, the differences are pretty incredible. But so that's my talk today on just computer basics, and thanks for checking in. And I'll see you next time.